Hi everyone, I'm Maddie. This is going to be a bit of a change of pace because I've switched from the perceptual inference session to the causality session, but I think you'll see that this work has actually quite a lot to do with causal modeling. So I'm going to be talking today about modeling auditory scene analysis as Bayesian inference in sound source models. So we'll start by listening to an auditory scene. It's going to be busy and maybe unfamiliar, but just do your best to try to tell what's going on. Alright, so I'm guessing that you heard many different instruments. So maybe a piano, a flute, a man singing, and some of you might have heard footsteps. And that all might have led you to the conclusion that this was an orchestra tuning up, and that would be a really good guess. It's actually someone walking through the hallway of a music conservatory, recording the sounds of the musicians practicing in the rooms adjacent to that hallway. And so, despite how busy it was, and maybe you never heard this kind of sound before, you were able to perceive these meaningful basic units, these sources of sound. But that source structure isn't evident in the sound waveform, nor is it evident in the spectrogram, which is a time-frequency representation of sound. Rather, perception has to construct those meaningful units, explaining these signals in terms of their causes, these sound sources. But since there are infinitely many causal explanations for this signal, the auditory system has to have some tendencies towards modeling certain types of source structure over others. And auditory researchers, since about the 1960s, have been trying to describe those tendencies as a set of Gestalt-like heuristics that the auditory system putatively uses to parse auditory scenes. And I'll give you an example of one of those through an analogy to the visual Gestalt principle of good continuation. So when we see this kind of figure, we tend to understand it as a long black bar connected behind that gray bar, rather than two shorter black bars exactly abutting the gray bar, or even these bent bars, even though all of those world states lead to the same figure. And the exact kind of continuity effect occurs in hearing. When you have a tone that's physically separated by bands of noise, you should hear the tone continuing through. So just pay attention to that tone and see what happens. All right. So while this work was tremendously productive in terms of coming up with this set of auditory illusions that at once demonstrated the ambiguity of auditory scenes, as well as potential tendencies that the auditory system might have in understanding them, these heuristics are really vaguely stated, and they can't actually be used to predict perceptual organization from sound. And so there have been many attempts at modeling aspects of auditory scene analysis, but as I see it, there are a few limitations to these. So some of these models depend fundamentally on there being a fixed number of sound sources in a scene. Many of them address only this one class of auditory phenomena, namely perceptual grouping in tone sequences. And finally, some of these take as input a symbolic description provided by the modeler, rather than the sound wave, meaning that in some sense this isn't a complete description of the process of auditory scene analysis. So we'd like to move towards a more comprehensive account of auditory scene analysis, and to do that, we're going to expand on an approach that's present in some of these models, as well as in some models of visual perceptual grouping. So specifically, we're going to start with these two hypotheses. First, that those tendencies of the auditory system can be described as assumptions about sound sources and how they produce sound. And second, the logic by which the auditory system applies those assumptions to sound is a process of probabilistic inference. So we're going to define a world model in terms of sources, so sources like a river, a gurgling, or a sparrow, an owl, and we're going to define how those sources generate sounds to produce observations. And then, if we define prior probabilities over our world states, so for instance, how many sources there are, what kind of sources there are, and also a likelihood term that tells us how likely some observation is given a world state, then we can use Bayes' rule to flip around that arrow and infer likely world states from an observation. Now, this idea of perception as inference is very long-standing, but I think there are two main difficulties in applying it to a complex problem like auditory scene analysis. So first, what is that world that perception constructs? What should this world model be? And second, this process of Bayesian inference is practically very difficult because structurally different world states, so world states with different numbers or kinds of sources, might lead to the same observation. And so to get over this problem, we're going to combine two recent computational tools. First, probabilistic programs, and second, neural networks. And we're going to apply our system at first just to classic auditory scene analysis illusions. And I'd just like to state here that although in theory this idea of perception as Bayesian inference is really long-standing and maybe even taken for granted, there aren't actually that many examples of Bayesian modeling of human perception from the raw sensory signal. And furthermore, what we'd really like to get at is what kind of simple assumptions do we have to make, and do those assumptions generalize? And one of the ways that we'd like to generalize is we want to be able to apply our model to natural scenes, natural auditory scenes. And I hope I'll show you how we're planning to do that. So first, I'll explain what probabilistic programming is, tell you a bit about that. So here's a simple graphical model. If we observe that sound, we can infer the latent variables that describe the auditory scene. For instance, that there's an owl hooting and some river making some background noise. However, we don't, in general, expect there to be exactly one kind of bird in the auditory scene and exactly one kind of background noise. Rather, the auditory system has to infer both the number and the kind of sources that are present. And probabilistic programs are an extension of graphical models that capture this and allow us to infer both the structure of the explanation and the latent variables. And to do this, we're using WebPeople, which is a probabilistic programming language out of Noah Goodman's lab. So with this first computational tool, I can now tell you what the world model is by defining it through a set of probabilistic choices. So I'll run you through that right now. So first we sample a number of sources, and here we've sampled just a single source. And then we sample its type, which it could be a noisy source or it could be a kind of tonal source. Here it's a tonal source. And then we sample its parameters, as well as a number of elements, which you can think of as musical notes. So here we've sampled 3 elements, and I'll play you what one of those might sound like for a tonal source. Just a tone. Now, given that whole set of sampling statements, this defines a prior probability over this world state. And since this is a symbolic description of a world state, we can now generate the sound that that source makes. So this tonal source might make this sound. And then represent it as a cochleogram, which is just like the spectrogram that we saw earlier, except it's based on the filtering properties of the human ear. And so that gives us our auditory scene. So I'll go through this again, but what happens if we have more than one source? So here we've additionally sampled a noise source. It makes a sound like this. And now we simply add those sounds up to get our final scene. All right, and what do we do if we want to make an observation? We simply measure the similarity of those 2 cochleograms, and that gives us our likelihood. Okay, so you can see that if we do inference in this model now, we have our likelihood, we have a prior. We're going to infer the number of sources, the sequence of sounds that each source makes, and the parameters of each source. So I'll talk about those source models now. For tonal sources, we simply parameterize them with a Gaussian distribution, and the frequency of each of the elements, each of those musical notes, is sampled from that Gaussian. So what you can see is that the source model for tonal sources prefers those elements to be closer together in frequency rather than further apart. And for noisy sources, we started from the observation that in natural sound, when you have noises, if you look at their frequencies that are closer together, those amplitudes tend to be more correlated than if they're further apart. And we formalize that by sampling noise spectra from a Gaussian process that, with an exponential kernel. So those correlations fall off as the frequencies get more distant. So that's our entire world model. So now we can do inference, but of course there's a practical difficulty of actually implementing our inference method. And this is so difficult because we need to search this huge space of very structurally different world states. And so to actually enable us to do inference, we trained a neural network on samples from our prior to put bounding boxes around the elements in those samples from the prior. And what we're going to do is use those bounding boxes to initialize our Markov chain Monte Carlo inference. And I'll show you an example of that in a second. So this is our second recent computational tool. All right, so we're going to start by looking at some perceptual data and start with this very commonly modeled genre of illusions, grouping in tone sequences. And I'm just going to show you one example. There are many of these kinds of illusions, but I'll just show you one. So this is what something like that might sound like. And this signal could have many different causal explanations. So it could be produced by two sources, one of which descends and then ascends, and then the other that does the opposite. We can call that the bouncing hypothesis, bouncing sources. Or it could be, again, produced by two sources, but these sources cross in frequency. Or in general, there could be an infinite number of other explanations. But humans tend to hear this explanation. And so I'll try to show you that now. What I'll do is play you the mixture, and then play you the bouncing source hypothesis, and then I'll play you the mixture again, and then play the crossing source hypothesis. And what you should be able to hear is that it's easier to recognize that you heard this bouncing source in the mixture than this crossing source in the mixture. So here goes the bouncing source hypothesis. Play that one more time. And now the crossing hypothesis. Alright, so I hope you could hear that distinction. How does the model do? It also infers these bouncing sources. And the reason it does that is because the tonal source models prefer elements that are closer together in frequency rather than further apart. Now, a lot of other models, like the ones I was talking about at the very beginning of this talk, also explain illusions like this in a very similar way. But what you should remember here is that we're actually doing inference from the waveform. And what you can think of this as is just a first test that our inference procedure is actually working. And I'll show you how it actually does that. So here's a cochleogram again. You've been seeing this of that sound, of that tone sequence. If we give this to the neural network, it'll put bounding boxes around those tones, and then use those bounding boxes to randomly initialize those tones across different sources. So these are hypothesized sources that potentially make up the scene. And then if we add up the sounds that those makes, that gives us our complete scene, and we can compare that to the observation in the likelihood, to compute the likelihood. And so I'll run MCMC inference now. And what you can see is that MCMC shuffles these tones around. Now it's found this two-source explanation, and you can see that it's in a mode, it's kind of just staying around there, and that's the bouncing explanation. All right, so we can do inference from the waveform, and now I'm going to show you another kind of genre of auditory illusions called perceptual filling-in illusions that will show you, hopefully, that this model can account for multiple classes of phenomena. So we've already seen one of these, the continuity illusion that we heard at the very beginning. And if you have a tone that is interrupted by a loud noise, which we'll call a masker, then there are many possible interpretations of that scene. And in particular, the auditory system has to fill in what happens to the tone while that masker noise is present. And now, masking can also occur in frequency, and so the auditory system in that case would have to fill in the spectrum of the sound that was masked. So we'll start with occlusion in time. I'm going to play you another type of continuity illusion. What you can see is that there are four figures here, very similar, except what's different in each one is that the noise gets quieter. So for the first two, you should hear one long tone, you should hear the tone continuing through the noise, and for the last two, you should hear pairs of short tones. All right, and if we look at the sources inferred by the model, what you can see is that it qualitatively captures this perceptual organization. And the reason that it does that is because when the noise is loud enough to mask the tone, the model prefers the simpler explanation of one tone, and when the noise gets quiet enough, the sensory evidence is basically overwhelming that the tone turns off and then turns on again. All right, so on to the occlusion frequency. I'll first tell you how McDermott and Oxenham measured perceptual filling in their listeners. So they played them this mixture sound, which was composed of a long masker tone and then a short, masker noise and a short target noise. It sounds like this. And then they got their listeners to adjust an isolated, short comparison noise until it sounded like the target. And the way that the listeners could adjust this noise was by either increasing the amount of energy in that middle band, which would sound kind of dull like this, or decreasing it, and so it sounded brighter like this. All right, so the way that we got our model to make comparisons to these listeners is we just gave it that observation, and we had it infer sources, and then we measured the amount of energy it put in that relevant middle band, the band that the listeners were adjusting as well. And so that's what's plotted on this y-axis here, and you can see that for a range of stimuli, the model is in good agreement with listeners. And in particular, for this kind of canonical example that we've been talking about, both listeners and the model put, about 20 decibels of energy in that middle band. So they're doing this perceptual filling in by adding that extra energy. And the reason that the model does this is that, remember, it prefers frequencies that are close together to have correlated amplitudes. And so, to an extent, the model makes that middle band match the outer bands, which aren't masked. Okay, finally, I want to show you how this approach might extend to some natural audio. So I got a recording of a sparrow, an owl, and a stream, and I put them together, and that sounds like this. All right, and if you give that sound to the model, and it comes up with a scene, this is the sum of all the sources that it infers. And that sounds like you'll recognize it as the scene that you just heard, except it's a little bit less musical, you could say. All right, so of course the real test of this is whether it infers these perceptually natural sources to us, and indeed it does. So you can see it groups those high frequencies together into this sparrow sound, the low frequencies together into an owl sound, and then it has this constant stream sound in the background. All right, so what I've shown you so far, these few illusions, this natural sound, to me are just really the first steps in this modeling endeavor, a proof of concept that inference in a generative model like this could underlie auditory scene analysis. And to do this, we incorporated a neural network into the inference procedure for our structured probabilistic program, and this allowed us to get past some of the previous limitations in some previous models. Now, what we'd like to do next is push our model to quantitatively explain the full and quite diverse set of auditory scene analysis illusions that are out there. And then, given that model, hopefully predict some new perceptual phenomena. So new illusions, yes, but also we want to be able to make more predictions in more ecological domains. So for instance, predicting when human listeners might find it difficult to parse a natural auditory scene. And throughout all this, I'm quite excited to explore both the merits and the limits of Bayesian inference as kind of this general principle of how our perceptual systems make meaningful structure out of raw sensory data. So with that, I'd like to thank my lab and my collaborators, and particularly Luke Hewitt, who is a graduate student and he's also at this conference. We have a project website. There are sound demos and some model results up there. Not any code yet, unfortunately. So if there are any questions, I'd love to take them. Thanks.